The biggest bucket chain excavator ever built weighs 6,000 tons and cuts material at 10,000 cubic meters per hour. The largest hydraulic shovel runs on 4,020 horsepower and is assembled outdoors because no factory can ship it whole. Across the machines explored here, bearing seats were machined to micron-level precision, windings were sealed under vacuum, and bucket teeth were shaped to sharpen themselves as it wears down. How each of those decisions is made, from the geometry of a single bore to final commissioning at the mine, will be explained ahead.
A mining machine does not start its life in a quarry. It starts on the floor of an assembly plant, where flat steel and bare castings are turned into something heavy enough to break rock. A construction machinery assembly plant covering roughly 50,000 square meters splits its operation into a components hall and a final assembly line. Inside the components hall, undercarriages, booms, and arms are fabricated from raw steel. Light subassemblies are tack welded together, then finished either by hand or by welding robots. Final inspectors check every joint before parts move on. Surfaces are sanded smooth and filled with body putty before painting. Lean manufacturing methods were introduced to cut waste from the process, eliminating standing inventory by producing to customer orders rather than to a warehouse target. On the main assembly line, both crawler and wheeled excavators move through configuration stations, where cabin options, hydraulic systems, and undercarriage choices like track shoe width are added. Every completed machine goes through hydraulic leak testing and pressure verification before final cosmetic inspection clears it for delivery.
Standard process sheets move between factories so that a machine built in one country matches one built elsewhere. At a Japanese plant producing intelligent machine control excavators, production is divided into parallel assembly lines that meet at a docking station. On the track frame line, technicians install rollers, while robotic equipment mounts the swing circle. Final drives, idlers, and crawler tracks are fitted in sequence. On the revolving frame line, workers install the main hydraulic valves, hydraulic oil tank, engine, and exterior panels. The two assemblies come together at the docking station, where the upper structure is lowered onto the track frame and secured. The excavator then moves down the main assembly line, where the swing machinery, boom, arm, counterweight, and bucket are installed. Large components are added in a carefully planned order to simplify alignment and testing. Each machine undergoes mechanical inspections covering hydraulic performance and movement functions before shipment approval. A central operations center monitors production and sales planning across the global network in real time, helping keep manufacturing schedules synchronized between facilities and ensuring machines are built to the same standards worldwide.
A mining excavator is the sum of every weld, every bolt torque, and every CNC cut that came before it. And the factory has to build quality into each one of those steps, not check for it at the end. Inside a UK production facility that has delivered more than 60,000 units to date, raw steel plate is moved by overhead crane into the fabrication area. Robotic welding, combined with manual finishing, forms the main frame. Each frame is then stamped with a grid matrix identification code by hand for full traceability, before being moved to a CNC machining center for precision boring and drilling of bearing seats and bolt holes. Step guards and side panels are fitted before the frame enters a sealed booth for high-pressure protective paint application. Coating thickness and adhesion are measured immediately after. The engine subassembly takes place in a dedicated cleanroom, where fuel lines, wiring harnesses, and ancillary components are connected before the engine is craned into the engine bay. The slew bearing is mounted onto the lower undercarriage, the steel track is laid out and pressed closed, and the upper structure is craned onto the lower carriage to complete the basic machine.
Behind every mining excavator is an engine, and behind every engine is a dedicated plant that machines, assembles, tests, and certifies it before it ever sees a chassis. A petroleum engine center covering 123,278 square meters has handled engineering, assembly, testing, painting, and shipping under one roof,
producing the 3500, 3600, and C280 engine families. The block test and machining stations rough machine each engine block under continuous coolant spray, then send the part for crankshaft inspection where laser scanning checks the surface for the smallest fault. Robotic rod machining lines handle the connecting rods in parallel. Crankshaft installation on the 3500 line combines robotic arms with overhead lifting to seat the shaft into the block, where automatic multi-spindle nut runners torque the main bearing caps to specification in a single cycle. Pistons and rods are pressed into the cylinders. On the larger 3600 line, heavy-duty cranes and 2 engineer alignment teams handle a crankshaft heavy enough to need its own lifting plan. Every completed engine runs a full on-site test under instrumented conditions. Pressures, temperatures, and output are monitored from a control room before the engine moves into the robotic paint booth and on to final shipment.
Some mining machines never see daylight. They live underground, cutting hard rock face by face, and they are designed at a facility built around that exact problem. A German production facility serves as a global mining headquarters for underground longwall and hard rock cutting products. The site invented activated undercutting technology and continues to develop the rock straight and rock flow systems that mechanize hard rock extraction. Inside the production hall, CNC machining centers cut large structural components to micron-level tolerances. Sensors measure each finished part for dimensional accuracy. High-pressure hydraulic blocks and power modules are assembled by hand. A longwall automation team develops the control software and sensor systems that allow these machines to run with operators kept clear of the working phase. A dedicated training center on site houses simulator cabs for both cutting systems.
Some machines are too big to ship in one piece. They are too big even to leave the factory in one piece, so the factory has to come to the mine. A hydraulic mining shovel was shipped from Germany in 12 sub-assembly groups and arrived at the open pit. On-site assembly began with the crawler tracks being lifted into position and mated to the chassis frame. Roughly 1,750 hours of skilled labor went into the build. The swing circle and mainframe were lifted onto the tracks by 2 heavy lift cranes working in coordination. The operator cabin and engine module were lowered onto the platform. Fully assembled, the machine weighs 750 tons. Its fuel tank holds 13,900 liters, enough for 12 hours of continuous high-load operation. The boom was craned into position and pinned to the front of the upper structure. Around 150 wiring harnesses were installed, connecting 4,000 individual wires across more than 12,000 meters of cable. Inside the engine bay, 2 heavy diesel engines deliver a combined raw output of 4,020 horsepower. The assembled shovel performed swing, boom, and bucket tests in the build yard before driving itself to the active mining cut.
Inside an underground mine, every drop of fuel and every degree of heat the machine puts out carries a cost to ventilation, to the operators, and to the bottom line. So the engineering brief reaches back into the factory and shapes the drivetrain itself. A hybrid diesel load-haul dump series uses an electric drive layout instead of a conventional mechanical transmission. During propulsion, diesel energy is converted to electric energy by an SR generator that powers the wheel motors. During braking, the energy flow reverses. The motors act as generators and feed energy into a kinetic energy storage unit. When the operator accelerates again, the stored energy is released alongside the diesel output, effectively combining a 400 horsepower engine with a 550 horsepower boost. The result is faster acceleration, lower fuel use of up to 30%, and a typical productivity gain of up to 20% in block cave mining cycles. Removing the transmission, torque converter, and differentials reduces maintenance demand and increases machine availability. Operator controls reduce to a simple forward and reverse switch, with no gears or clutch to learn. From the factory floor onward, the drivetrain is designed for high-production hard rock applications and for machines that will spend their entire lives underground.
Not every mining machine moves on tracks. Some are continuous miners, purpose-built to cut, gather, and haul material in one motion, and engineered from the factory for the exact rock conditions they will face.
A heavy-duty continuous miner designed for industrial minerals applications reaches a 6-meter cutting height with a retractable cutting drum for fast repositioning between faces. Total installed power reaches 910 kilowatts. The machine weighs 154,000 kilograms, sized to remain stable under the sump and shear forces of an industrial mineral seam. Its modular design allows the unit to be broken down and reassembled inside underground workings where no surface crane can reach. Alongside it, battery haulers run on lithium-ion packs that recharge in 2.5 hours, replacing diesel haulage and eliminating exhaust emissions in confined ventilation. A flexible conveyor train can haul up to 36 tons per minute behind a continuous miner, autonomously following its movement through the cut. The truck that hauls ore out of an open pit has to handle 28 tons of payload on a road that did not exist last week, and the entire chassis has to be designed in the factory for that abuse. A 30-ton class articulated dump truck combines a 248 kilowatt diesel engine producing 332 horsepower at 2,000 revolutions per minute with an operating weight of 25,395 kilograms and a heaped body capacity of 17.1 cubic meters. The articulation joint between cab and dump body lets the truck pivot on uneven haul roads where a rigid frame would lose traction. Hydropneumatic suspension absorbs shocks from rock-strewn surfaces, protecting both load and driver. A proprietary traction control system distributes torque between axles based on real-time wheel slip. Selectable working modes let the operator trim output for terrain and fuel economy. Wide, low-profile tires keep ground pressure manageable on soft surfaces. The operator cabin integrates rollover and falling object protection structures directly into its frame, with a rear-view camera and an automated transmission for smooth shifting under load. Every system is matched to the punishment the truck will take across thousands of haul cycles.
At full assembly, the scale becomes hard to take in. A mining shovel rated near 1,000 tons operating weight runs on dual engines, producing roughly 2,200 horsepower each. The bucket holds 35 to 50 cubic meters of material per pass, depending on configuration. Its hydraulic system drives digging and lifting at output levels that would tear apart a smaller frame, with structural components built from high-strength steel sized for the cycle loads of a continuous mining operation. Once these machines leave the factory, the test is no longer dimensional accuracy or paint coverage. The test is the job site, and the proof is the cycle. At a marble quarry, an off-road dump truck reverses into position alongside finished marble blocks cut into precise rectangular shapes. A large wheel loader, fitted with tire chains to protect rubber against sharp stone, advances into the working area. The loader scoops crushed stone and earth into the truck bed first as a cushioning layer. The truck shifts position to balance the load before the next bucket comes in. A second dump truck enters the cycle. Other loaders work nearby, moving large marble blocks to a separate stockpile. The coordination between machines runs continuously, each unit handling a defined part of the cycle without interruption. Everything visible here, chassis, hydraulics, drivetrain, cab, came off a factory assembly line built around exactly this kind of duty.
A mine does not run on one machine, it runs on a fleet, and the largest members of that fleet are built at a scale that makes everything else on site look small. The RK5000 bucket chain excavator weighs 5,600 tons, stretches 160 meters from end to end, and rises 40 meters above the mine floor. Its hydraulic movement system holds 15,000 liters of oil. Maximum output reaches 4,450 cubic meters per hour, sustained by 6 operators working across the machine simultaneously. The entire structure moves on a crawler undercarriage, turning and repositioning its speed slow enough that the ground deforms visibly under the load. Built in 1983 and overhauled 3 times since, the RK5000 is not assembled at a factory and delivered whole. It is built where it will work, and it stays there for decades. Moving it at all is a separate engineering task. Time-lapse footage of the machine relocating between mine zones at Komarani in the Czech Republic shot at between 100x and 300x speed, reduces weeks of movement to minutes. Even compressed, the machine barely seems to move. The upper structure rotates slowly while the crawler system inches forward on mud, pressing ruts deep enough to walk in. Cable drums trail behind to manage the power supply moving with it. Getting a 5,600-ton machine from one zone of a mine to another is not a transport job. It is a construction project in its own right, and it runs on the same logic as the excavation itself: slow, precise, and continuous.
The RK5000 is large. The K10000 moves past large entirely. With a theoretical output of 10,000 cubic meters per hour, a cutting height of 35 meters, and an operating weight of 6,000 tons, the K10000 operates at a scale where individual components, the cable bundles bracing the boom, the slewing ring at the base, the chain of buckets working the face, are each large enough to be construction equipment in their own right. The machine's cutting arm extends 70 meters from the machine axis in either direction, rotating a full 360 degrees on a walking chassis that repositions the entire structure as the mine face advances. At this output, the K10000 does not load haul trucks. It feeds a continuous belt conveyor system running directly from the discharge end of the machine. Water suppression vehicles track along the conveyor lines to control dust. Two operators on the deck manage the machine from above while at work.
Watching the geared chain work against a mine face makes the scale of this machine real in a way that specifications alone cannot. The RK5000's bucket chain hangs from a long boom angled down toward the coal seam. As the boom lowers to match the terrain, the chain cycles continuously, each bucket scraping material from the face, carrying it up the boom and tipping it onto an internal belt that runs the length of the machine toward the discharge end. The slewing gear at the base rotates the entire upper structure to sweep the face across a wide arc before the crawler system advances the whole machine forward to begin the next cut. At the discharge end, material drops from the belt directly onto a mobile receiving unit, a tracked transfer machine running alongside, which feeds the next stage of the belt conveyor network. The internal belt, the slewing gear, the crawler tracks, and the bucket chain are all running at once, continuously for as long as the machine is producing. A maintenance crane on the upper deck allows work to continue on mechanical systems while the machine is in operation. The hydraulic movement system that controls positioning, slewing, and boom angle circulates through 15,000 liters of oil, the volume of a small tanker truck, keeping every actuator in the system responsive across the full range of operating conditions.
The continuous mining principle scales down as well as it scales up, and at smaller scale, the same logic becomes mobile. The K100 compact bucket wheel excavator weighs 74 tons and produces up to 500 cubic meters per hour, with an effective sustained output of 200 cubic meters per hour. A rotating wheel fitted with buckets around its circumference cuts material from the face. That material drops onto a conveyor belt running along the boom and transfers to a discharge boom that feeds the next conveyor in the chain. The bucket wheel drive is electromechanical, eliminating diesel exhaust at the working face entirely. The machine moves on a crawler undercarriage and requires no significant disassembly for transport between sites. At shore approaches, river margins, or quarry zones where a full-scale excavator cannot maneuver, the K100 works continuously without the stop-start cycle of a hydraulic grab machine. The boom lift and discharge boom are both hydraulically driven, with a permanent central lubrication system maintaining the slewing gear, undercarriage components, and main drives throughout operation. Because undercarriage parts, conveyors, slewing gear, and main drives all use standard components, replacement parts are available without long lead times, a practical constraint that shapes how any machine used in continuous production must be designed from the beginning.
Where bucket chain excavators advance steadily across vast mine faces, hydraulic excavators focus on flexibility and fast truck loading. The R9400 is a 345-ton backhoe excavator delivering 1,250 kilowatts at Trapper Mine in Colorado. The site previously used wheel loaders in this area, but moved to a hydraulic excavator after evaluating availability and compatibility with its 240-ton haul trucks. Within 3 months of entering service, production at the loading face increased by 40%. The bucket was designed specifically for this machine to operate near the maximum rated suspended load, allowing the hydraulic system to deliver high productivity on every digging cycle. Efficient bucket filling and truck matching are critical because even small delays can reduce total material moved over a shift. A well-matched loading system keeps trucks moving instead of waiting at the face. Operating conditions are demanding throughout the year. Temperatures range from winter wind chills of -40 degrees Celsius to summer highs above 37 degrees Celsius. A dedicated cold weather package allows the excavator to maintain reliable operation through severe winter conditions. The machine is expected to perform consistently despite dramatic seasonal changes. Every digging cycle presents a different challenge. Material hardness changes with geology and moisture. Truck positions alter swing angles, and ground conditions evolve as mining progresses. These constantly changing forces are carried by the boom, stick, bucket, and pin assemblies under full hydraulic load, shift after shift.
An excavator that has worked a mine long enough eventually tells you exactly where the loads went. The CAT 345B rebuild sequence begins with stripping the undercarriage of hardened mud and worn components, grinding mating surfaces back to specification, and replacing track chain, rollers, and idlers that have absorbed thousands of dig swing dump cycles. The hydraulic pump assembly and control valves are pulled apart to measure internal wear on surfaces that carry pressure every time the bucket hits resistance. Every fastening torque is re-established. The frame, boom, and stick are inspected for fatigue cracks at the weld toes and pin bores, the exact locations where bending and torsion concentrate during hard digging. Anti-corrosion primer goes on before top coat, and every layer is applied to surfaces that were ground clean first. The engine is reconnected to the hydraulic system and run under load to verify pressure curves before the machine is signed off. A certified rebuild returns the machine to factory specification at substantially lower cost than a new unit. The practical result is a machine that re-enters the dig rotation with the same rated performance as the day it was first commissioned, because the specific components that absorb the highest cumulative load have been replaced, not patched.
A wheel loader works differently from an excavator, and its structure reflects that difference at every joint. The XC9350 carries a rated load of 35 tons on a frame that articulates at the center, allowing the front and rear sections to angle independently for tight turning in confined loading zones. The bucket mounts to a hydraulic lift arm that raises the full load from ground level to discharge height in a single continuous stroke. The bucket teeth shown in close-up are designed for the specific material hardness of the application. Worn teeth reduce penetration force and increase the cycle time across the entire shift. The rear section carries the engine and counterweight, balanced against the front load on the articulation joint. At 35 tons of rated payload, the hydraulic system generating lift and crowd force is the same class of equipment found on mining excavators, scaled for a machine built around speed of cycle rather than depth of cut.
The excavator loads the truck. The truck then moves that material across the mine as quickly as road conditions allow. The T282C carries 363 metric tons and reaches speeds of up to 64 kilometers per hour. Its diesel-electric Litronic Plus drive system automatically manages engine output to match load and gradient, improving fuel efficiency while maintaining productivity. The frame is designed to deliver high payload capacity without unnecessary weight, giving the truck an excellent payload-to-vehicle weight ratio.
Suspension performance is tested using real operating data collected from mine sites. Engineers replayed these load conditions on dedicated test equipment to evaluate ride quality and structural response before any design updates are approved.
Before any of these machines can work a mine, they have to get there. And for the largest of them, that journey is an engineering problem before it is a transport problem. The LoadQuip SW450 is a 450-ton capacity low loader transported to site in 3 main subassemblies and reassembled on arrival. The assembly sequence uses overhead cranes and precision alignment to join the main frame sections, fit the gooseneck, and install the rear axle group. Processes involving line boring and liquid nitrogen shrink fitting to achieve the required tolerances at each major joint. Once the prime mover connects to the trailer for the first time, swing wheel steering and main deck jacking are tested before the unit enters service.
Tracks, teeth, buckets, undercarriage, these are the parts that hit the rock, wear out fastest, and decide whether a 590-ton machine earns its place in the pit or sits idle waiting for repair. A front shovel of this class arrives at the mine in pieces. The 6060 FS front shovel is the first of its line delivered to Mongolia, assembled on site at the OYU Tallgoy operation. Heavy haul trucks bring the components in through Zeeman Oud Port, where a crew of 11 technicians spends roughly 1 month assembling the machine. A mobile crane lowers the operator cabin onto the chassis. Crews install the tri-power digging system, hydraulics, drive chains, the boom, and the front bucket. Operating weight, 590 tons. Bucket capacity, 34 cubic meters. Gross power, 3,000 horsepower. Bucket payload, 61 tons. Engines, 23512C diesel units. After handover, the machine drives into the pit and begins loading haul trucks.
Every machine working on rock or stripped earth faces one first question: how to carry its weight without destroying the surface below it. Tracks answer by spreading mass across a long, wide footprint, and that choice shapes everything else on the machine. The principle scales upward into the largest crawler cranes ever built. The LR1135O is a heavy crawler crane equipped with power boom, a twin-boom system that handles loads beyond a single lattice's reach. In the Netherlands, an LR1350 with power boom lifts a 378-ton machine housing of the 6-megawatt class onto an installation tower 110 meters high. The power boom configuration allows the operator to bring the housing up on one hook at one angle in a single coordinated motion. Underneath the boom, the entire machine rides on 2 long tracks. Each plate, wider than a worker, is tall. The undercarriage spreads operating weight, counterweight, and lifted load across enough surface area to let the crane work on prepared ground without sinking or rocking under load. On a lift of this size, a few centimeters of track sink on one side would tilt the boom, shift the load center, and turn the rated capacity chart into a guess. The bigger the lift, the more carefully the ground beneath the crawler has to be inspected and leveled before the first hook is set.
Tracks solve the load problem. They also create a new one. How does a machine this heavy reach the site in the first place? This 500-ton class crawler crane is built around a single problem. The bigger the lift capacity, the heavier the machine becomes to move. The base machine of the LR1500 is engineered to ship at just 45 tons and travel within a 3-meter transport width. The crawler side frames detach completely and ride on their own trailers. The central crawler section is shipped as one piece. On site, the machine self-jacks off its transport trailer using built-in hydraulics, then reattaches the side frames through quick connection joints. The boom is built section by section, then locked together with automatic pin systems. Counterweights are placed using the crane itself. The control system inside the cab monitors load, radius, and boom geometry continuously. Every choice ties back to total cost. Less hauling, fewer permits, faster setup. This engineering logic governs every crawler-mounted machine that works at this scale. A giant mining shovel has to reach the pit too.
And once it gets there, the tracks beneath it have to carry the work day after day and year after year. From a machine that carries weight to one that pushes it, the job changes shape. The dozer lives in constant abrasion. Blade, ripper, and tracks all grind against the surface they work on hour after hour. Wear life is measured in how often steel gets replaced. The D11 is the largest production-class dozer in the heavy mining lineup. The new D11 delivers up to 8% more productivity, 8% better fuel efficiency, and 5% lower maintenance and repair cost. Every gain measured against cost per ton of moved dirt. Load-sensing hydraulics remove parasitic loads when there is no demand on the pumps, so the engine burns less fuel idle. A new fuel map combined with the new hydraulics raises production while cutting fuel use. The reverse drivetrain delivers 955 horsepower in third-gear reverse, which shortens shuttle cycle time. The blade has changed too. An extended U-blade, slightly taller and deeper than the standard U-blade, carries up to 42 cubic meters of material instead of 34. A single chassis now handles every application that previously required separate carry dozer and standard frames. The hood opens on hydraulic struts. Optional paired access ladders run down to the tracks. Every pinpoint on the machine is now greased with a bushing in-pin arrangement that drops scheduled maintenance. Total focus across the redesign, lowest cost per ton of dirt moved.
Every giant machine in the pit depends on a workshop behind it. Steel constantly wears down and has to be reformed. The big iron only keeps running because smaller tools sit ready to bend, cut, and reform the parts that take abuse. This electrically driven, hydraulically operated bending machine sits in that workshop role. It bends flat steel bars up to 100 by 14 millimeters with the heavier die, and up to 80 by 10 millimeters with the standard die. Pipe benders handle diameters from 15 millimeters up to 75 millimeters across two jig sizes. RHS sections of 25 and 38 millimeters can be formed on the number 1 jig. Thin wall tube benders cover stock at 12, 16, 20, 22, and 25 millimeters. A pipe notcher cuts saddle joints at 20, 25, and 32 millimeters with 40 and 50 millimeter options. Every excavator, dozer, and shovel in a working pit depends on this kind of small tool fabrication behind it. Custom guards for hydraulic lines and grease points get formed and welded. Bucket wear plates get cut and rolled. The visible giant in the pit only works because smaller hands and smaller tools are repairing the steel that wears out first.
From workshop steel back to the working face. After the shovel breaks rock free, the next problem is what to do with all of it. Rock leaves the mining face in pieces too large for any conveyor or processing plant downstream. First step, on-site crushing. The Locotrack family is a series of mobile crushing and screening plants mounted on tracks, built on crawler logic borrowed from the giant machines that fed them, adapted to a different job. The range runs from 30 tons to 850 tons, with the largest unit, the LT2200E, built around a C200 jaw crusher. Track mounting matters. A mobile crusher can follow the working face as the pit advances, reducing how far the rock has to be hauled before primary crushing happens. Smaller variants handle aggregates and recycling. Larger units serve hard rock mining. The newest concepts pair an impact crusher with a high-capacity single-deck screen and a return conveyor, all on one platform. A wireless control system lets the excavator operator feeding the crusher manage the plant from inside the excavator cab. The operator no longer has to climb down to adjust the crusher, which keeps loading cycles continuous and operator exposure lower.
Every mining machine runs on torque. The diesel engine is where that torque originates, and in heavy equipment, the margin between an engine that lasts and one that fails early is measured in 10,000ths of an inch. A diesel engine rebuild specialist in Tennessee, producing over 500 engines per year, has built its reputation on correcting the tolerance gaps that factory production lines leave behind. Using CNC honing, boring, and machining centers, the shop holds cylindricity and concentricity to tolerances finer than 1/15th of a human hair,
the level of precision that determines whether piston rings seal consistently across a full thermal cycle under load. Cylinder head work maintains valve seat concentricity for better sealing and higher combustion efficiency. Crankshaft balancers extend bearing and bottom-end life by reducing vibration at high torque output. The same precision standards that apply to on-highway diesel trucks become non-negotiable at larger scale. Cat 3500 16 blocks, Waukesha and MTU engines, the power plants found in large earth-moving equipment, marine applications, and mining machinery, are now processed through the same machining centers, applying the same surface finish standards to engines that produce vastly more power and run in conditions where an unplanned stoppage costs orders of magnitude more per hour than a broken-down road truck. In mining, engine downtime does not mean a late delivery. It means an entire fleet stops moving.
What happens inside an engine block when it runs under full load depends entirely on the geometry of the surfaces cut into it. Starting from a custom-forged aluminum billet weighing 386 pounds, CNC machining removes approximately 83% of the raw material, leaving 64 pounds of finished structure. Every bore, every passage, every mounting face is cut to a specific geometry. The bell housing side is machined first, then the block is flipped and the water pump face is completed. Custom end mills are ground to the required relief angle in-house when off-the-shelf tooling cannot reach the geometry needed. Cylinder sleeves are machined with cooling holes at the top and O-ring seats at the base, controlling both heat extraction and sealing at the combustion zone. The finished block weighs 17% of the starting material. In a large diesel engine for mining equipment, a Cat 3516 block machined on a center capable of handling that mass, the same logic applies at 10 times the scale. Each bore must be cylindrical to within the tolerance that allows the piston to seal on the compression stroke, and concentricity of the main bearing bores determines how the crankshaft loads are distributed across every revolution at full torque.
The diesel engine generates torque, but in many mining machines, that torque is converted to electricity before it reaches the wheels or the cutting system, and the quality of that conversion depends on what happens inside the generator. Large industrial generators and motors are built from silicon steel laminations stamped to a precise profile and stacked under hydraulic pressure to form the stator core. Stacking reduces eddy current losses that would otherwise convert electrical energy into waste heat at the core. Copper conductors are shaped into coils and wound into the stator slots by hand, with each slot lined with insulation material before the first conductor is placed. The rotor is assembled separately, balanced dynamically on a dedicated machine to eliminate vibration at operating speed, and then inserted into the completed stator with the clearance between rotor and stator bore held to a fraction of a millimeter. After winding, the entire stator assembly enters a vacuum pressure impregnation chamber. Resin is introduced under vacuum and then pressure forced into every gap between conductors and between conductors and the core, eliminating voids that would otherwise trap moisture or allow vibration-induced movement. The assembly is then cured in an oven. Every finished machine is tested on a load bank before leaving the factory. Voltage, current, insulation resistance, temperature rise, and vibration level all verified against specification. Inside every electric motor, the winding pattern is where power density and reliability are determined, and no two winding types are interchangeable. A large motor facility runs several winding processes in parallel across different production lines. Random winding of multi-strand stator coils fills the slot with continuously laid conductors, maximizing copper fill factor. Layer winding for rotating field coils places conductors in precise layers where magnetic geometry requires exact positioning. Exciter rotor winding drives a small generator whose output feeds the main rotor field, removing brush contacts in synchronous machines. DC armature rewinding removes old winding from the armature, prepares commutator segments, and re-insulates each slot. Slotting wedge locks each coil into its slot mechanically after winding is complete. Toroidal winding wraps conductor continuously around a ring core, used in transformer and motor designs requiring closed magnetic paths. Each winding method creates distinct electromagnetic behavior, and an incorrect choice prevents the motor from sustaining rated load. Final inspection includes insulation testing, thermal performance evaluation, and electrical continuity checks to ensure every coil can withstand rated current, heat, and long operational duty cycles in industrial applications without failure under continuous load conditions in practice today.
The traction motor in a diesel-electric haul truck is not a standard industrial motor. It absorbs the full braking and acceleration loads of a 363-ton vehicle hundreds of times per shift, and the armature is where that abuse accumulates. The Hytrax rewind process starts with removing the old windings and installing a new commutator. High voltage pressure and bar-to-bar tests confirm structural integrity before any new components are added. Each slot is individually insulated, after which Hytrax coils are inserted and precisely aligned with commutator segments. Slot wedges lock every coil in place mechanically. The assembly is then prepared for TIG welding with protective layers applied. Automated TIG welding fuses each commutator connection with precision. The armature enters a vacuum pressure impregnation cycle where resin is forced into all internal voids under controlled pressure and then cured. Once hardened, the winding is banded for centrifugal strength. A dial indicator checks runout before the commutator is skimmed on a lathe. Laser-guided undercutting machines the insulation between segments to exact depth, followed by diamond tool finishing for brush contact surfaces. Finally, dynamic balancing is performed, with correction weights added until specification is met. A complete inspection report is printed before release.
A mining machine may weigh hundreds of tons, but its drive system depends on a motor built around precise control of the stator winding. Production begins with slot insulation, where automated machines insert insulation paper into every stator slot to isolate the copper conductors from the steel core. CNC winding equipment then forms copper coils and inserts them into the stator without damaging the insulation. Intermediate forming compresses the winding ends to create the space required for later operations. Automatic lacing machines bind the winding heads with heat-resistant cord, preventing movement caused by vibration and magnetic forces during operation. Final forming aligns the entire winding assembly and maintains the precise air gap required between stator and rotor. Before the stator moves to assembly, automated testing verifies electrical resistance, insulation quality, and the absence of short circuits. Every step is designed to prevent failures that may appear only after thousands of operating hours. For large mining drive motors, the stator production sequence is the same whether the motor goes into an electric vehicle or a mine drive system. The automation simply changes scale. An integrator production line handles insulation paper insertion, 3 successive rounds of coil winding and embedding, pre-shaping and fine shaping between rounds, star welding to lock the phase connections, double-sided lacing to bind the winding bundle, terminal welding, and final slot expansion. QR codes track each core through every station. Manual alignment stations between automated cycles correct the coil geometry before the next embedding stage locks it in place. A final inspection checks the completed stator before it moves to the logistics line.
Remove the commutator, remove the brushes, and the wear mechanism that limits DC motor service life in a traction application disappears with them. A fully automated BLDC assembly line winds and inserts stator coils, hydraulically presses the stator core, robots handle the housing, and a press assembly joins rotor, stator, and housing into a finished unit without manual intervention at the critical tolerance stages. Sensors verify position at each transfer point. The completed motors exit the line with power leads already connected, ready for electrical testing. The absence of brush gear means the only wear surfaces remaining are the bearings, a fundamental change in the maintenance profile of the drive system.
An engine that has sat for 32 years tells you everything you need to know about what thermal management actually costs when it fails. During the second start attempt, the R335O produces oil smoke, suffers primer pump reversal, and reaches cylinder head temperatures high enough to force shutdown. In mining equipment, the same chain of events means lost production, inspections, and delays. Cooling, lubrication, and thermal monitoring systems exist to prevent it.
The last piece of the drive system is the motor that actually turns the load.
and starting a 3,000 kilowatt motor under heavy inertia is a different engineering problem from running it at steady state. A three-phase asynchronous slip ring motor rated at 3,000 kilowatts and 10,500 volts takes 90 seconds to accelerate from standstill to 993 revolutions per minute on a test bench. The slip ring design allows external resistance to be connected during startup, delivering high torque from zero speed while limiting in-rush current. This makes it suitable for heavy-duty applications such as cement mills, mine compressors, and large industrial fans. A Yokogawa power analyzer tracks voltage, current, and frequency throughout the test. Including its cooling system, the motor weighs 13.5 tons and is built for demanding industrial duty.
Getting a machine to a mine is not a single operation. It is a chain of logistics decisions, each one constrained by the one before it. The Liebherr R9800 mining excavator arrives at Port Kembla, New South Wales, in the hold of a large cargo vessel, broken down into the oversized components that no road system could carry assembled. Cranes at the port work through the night to lift each section from the ship and lower it onto multi-axle heavy transport vehicles staged along the dock. The convoy then begins the road movement from the coast, routing through Sydney and north to the Boggabri coal mine, a journey that requires route surveys, clearance checks at every bridge and underpass, and coordination with road authorities for each segment. At the mine's assembly area, two large mobile cranes work in combination to lift and position the structural components in sequence. Assembly runs day and night under high-intensity lighting because every hour the machine sits unfinished is a cost against the project's schedule. The sequence follows the logic that every mine site assembly must follow. Base frame and undercarriage first, establishing the foundation on which every other component will load. Then the upper structure and slewing ring, then the boom and stick, then the engine and power unit, then hydraulic lines and electrical systems, then the bucket and attachment last. Commissioning begins before the final components are fitted. Hydraulic systems are pressurized and checked for leaks, electrical systems are verified, and the slewing and travel functions are tested under controlled conditions at the assembly area. Only after the full commissioning sequence is complete does the R9800 move under its own power into the open-cut bench and begin loading haul trucks. The structural steel fabricated for mining and port infrastructure follows the same assembly logic as the machines themselves. Components are made to a design, transported to site, and joined in a sequence that cannot be reversed. A steel construction specialist produces overhead cranes, stacker reclaimers, harbor loaders, silos, pipe cranes, and industrial frameworks as prefabricated sections ready for installation. Before leaving the workshop, each section receives machined connection points, lifting lugs, and bolt hole patterns built to precise tolerances. Any correction work performed high above the ground or inside a confined industrial site is costly and time-consuming, so accuracy must be achieved before shipment. In mine maintenance workshops, overhead cranes are assembled only after runway beams are level and parallel. Errors at this stage affect every lifting cycle throughout the crane's operating life. Stacker and reclaimer systems arrive in multiple sections and are erected from the base upward, with alignment verified at every connection before the next section is installed. Gangways, access bridges, and overbridges are often delivered as completed modules to reduce site work and installation time. By the time the finished structure begins operating, the most important quality decisions have already been made. They were determined in the fabrication shop at the cutting table and welding station, long before the steel ever reached the site. The structural steel fabricated for mining and port infrastructure follows the same assembly logic as the machines themselves. Components are made to a design, transported to site, and joined in a sequence that cannot be reversed. A steel construction specialist produces overhead cranes, stacker reclaimers, harbor loaders, silos, pipe cranes, and industrial frameworks as prefabricated sections ready for installation. Before leaving the workshop, each section receives machined connection points, lifting lugs, and bolt hole patterns built to precise tolerances. Any correction work performed high above the ground or inside a confined industrial site is costly and time-consuming, so accuracy must be achieved before shipment. In mine maintenance workshops, overhead cranes are assembled only after runway beams are level and parallel.
Errors at this stage affect every lifting cycle throughout the crane's operating life. Stacker and reclaimer systems arrive in multiple sections and are erected from the base upward, with alignment verified at every connection before the next section is installed. Gangways, access bridges, and overbridges are often delivered as completed modules to reduce site work and installation time. By the time the finished structure begins operating, the most important quality decisions have already been made. They were determined in the fabrication shop at the cutting table and welding station, long before the steel ever reached the site.
Before a heavy component can enter service, it has to be assembled to the tolerances the application demands, and verifying those tolerances under load is a different task from verifying them on a bench. A specialist assembly facility uses a test pit 8 meters wide, 8 meters deep, and 11 meters long, built on solid rock with effectively no weight limit. Components up to 16 meters tall are assembled inside the hall, while larger units can be handled by opening the roof and using mobile heavy lift cranes. Assembly methods include bolting, welding, and shrink fitting using hot plates, induction heating, or dry ice depending on the required fit. Once assembled, components undergo static pressure testing at up to 600 bars to verify structural integrity. Dynamic testing then reproduces the pressure cycles, bending loads, and rotational forces expected during operation. A component leaves the facility only after passing every functional test. The reason is simple. A joint that survives a static test may still fail under repeated working loads, and in mining operations, that failure can stop production for entire shifts.
Every cycle a mining excavator completes ends the same way. The bucket teeth hit rock. That contact point is where all the engineering upstream, the factory, the assembly, the hydraulic system, the structural frame, is tested against the actual material being mined. The ZG3 tooth system is a ground-engaging tool designed for hydraulic mining excavators up to 400 tons, and its design reveals the philosophy that governs every sacrificial component in mining equipment. The tooth is intended to wear. A self-sharpening tooth edge maintains penetration performance as the wear surface recedes, so the digging force required per pass stays consistent across the tooth's working life, rather than climbing as the profile blunts. An improved wear material ratio extends service life, reducing replacement frequency and the downtime each replacement represents. The adapter behind the tooth carries the structural load. A redesigned nose with a large contact surface distributes load symmetrically, reducing plastic deformation at the mating faces. A spherical front design allows slight tooth movement during digging, which clears fine material from between components and prevents packing that would lock the assembly. An integrated wear indicator shows the replacement point without inspection guesswork. The tooth signals when it needs to change. The locking system requires no hammer, 2 steps, an acoustic confirmation click, and the tooth is secured. Removal follows the same sequence in reverse. In a mine running multiple excavators across 2 or 3 shifts, the cumulative time saved across every tooth change on every bucket across every machine in a year is not a minor efficiency gain. It is a measurable reduction in total fleet downtime. The tooth is the cheapest part of the assembly. Designing it to be replaced quickly, correctly, and safely without tooling is the acknowledgement that in mining, the cost is never in the component. It is always in the time the machine is not working. Replacing the tooth is the easy maintenance. What happens to the rest of the machine when it works through conditions that no factory test can fully replicate is the harder question. Liebherr hydraulic mining excavators operate with standard bucket capacities up to 34 cubic meters, paired with mining trucks rated to 363 metric tons payload. In the field footage of open-cut mines operating under deep winter conditions, both machine types continue working through frozen ground, snow-covered benches, and temperatures that would stop most industrial equipment. The excavator cuts through material that ranges from loose overburden to consolidated rock within the same shift, with no adjustment to the structural parameters of the boom, stick, or bucket. The machine must handle both without advance notice of which is coming. Mining trucks operate on haul roads that change surface condition with every load cycle. Wet from blasting water, compacted by traffic, broken by heavy axle loads. Each truck absorbs the full payload impact on the tray at every loading pass, and the frame carries that load down grades where the retarding system is working continuously. Field crews shown working around the machines in winter conditions are performing the visual inspections, fluid checks, and component assessments that happen between shifts.
a machine that cannot be inspected quickly and safely in field conditions. Low light, cold, mud, confined access will accumulate undetected wear that turns into unplanned failures. The operational environment never simplifies. The design has to accommodate it from the beginning. The Quarry shows what the machines are actually up against, not as a test condition, but as the daily production reality. At the Cardinal Aggregate Quarry in Ohio, the extraction sequence begins before the excavator ever touches rock. Large excavators and articulating haul trucks strip the overburden first, removing the soil layer to expose limestone reserves. Through every 10 by 10 foot area of dirt removed, 1,600 tons of rock reserves become accessible. Drill rigs bore through solid rock at 5 feet per minute to prepare blast holes. Each blast produces between 15,000 and 25,000 tons of raw aggregate in a single event. The rock that reaches the crushing plant arrives in pieces up to 3 feet across. A jaw crusher reduces that material to under 10 inches. The processing plant then separates and sizes the output into up to 5 products simultaneously: road base, concrete aggregate, asphalt rock. On peak days, 400 trucks move through the loading and weighing process. The operation scales to 55 trucks per hour through the scale-out, producing 8,000 to 9,000 tons of finished product in a single day. Every machine in that chain, the excavator, the haul truck, the crusher, the loader, is absorbing abrasive material, impact loads, and vibration continuously. The jaw crusher in particular receives the most violent loading in the system. Every rock that enters it is being fractured by force, and the crusher's wear surfaces, liners, and jaw plates are consuming themselves in the process of doing that work.
The most expensive field failure is the one that stops the machine completely, and in underground work, getting to the machine to repair it is itself a major engineering project. During excavation of the State Route 99 tunnel beneath Seattle, the Bertha tunnel boring machine suffered damage to its outer seals. Repairing it required building a 120-foot deep access shaft from the surface to the buried machine and disassembling part of a 2,000-ton system underground. New bearing and seal components were manufactured, including a redesigned seal system that improved maintenance access. As repairs progressed, crews discovered additional problems. The center pipe required replacement, and damaged pinion gears in the cutter drive system were repaired at the same time. The cutting tool arrangement was also modified for the remaining drive. After reassembly, engineers performed a no-load test to verify hydraulic, electrical, and mechanical systems before any soil contact. Once the access shaft was backfilled and the machine was again surrounded by soil and groundwater, a load test confirmed performance under real operating conditions. Only after both tests were completed did the machine move forward again, advancing slowly for 430 feet before resuming normal tunneling. The repair effort lasted months and demonstrated a costly lesson. Maintenance access can be just as important as the component itself. The hydraulic excavator rarely works under identical conditions for long. Ground elevation changes, material consistency varies, and every movement demands a different combination of digging force and precision. Throughout this operation, the machine repeatedly cuts grade, reshapes the work area, handles heavy components, and repositions material while maintaining control on uneven terrain. The boom, stick, and bucket cycle continuously, absorbing loads that shift from soft soil to compacted ground within the same work zone. Hydraulic cylinders must respond smoothly whether the operator is making a fine adjustment or moving a full bucket of material. The undercarriage supports the machine as it works near slopes and excavated sections where stability becomes critical. Small positioning errors can affect every step that follows, so operators constantly verify alignment and elevation before continuing. The machine is not working at maximum production rate. Instead, it is performing the type of precise field work that depends on reliability, control, and repeatable hydraulic performance throughout the entire shift.
The underground environment removes every assumption that surface equipment operation allows. At the Victoria Road shaft, crews descend into an excavation 25 meters wide and about 30 meters deep, working far below the surface through confined access points.
The shaft combines 11 precast concrete rings with sprayed concrete lining extending to the bottom. For giant mining machines operating in underground mines, the challenge is similar. Hydraulic hoses, drive systems, pumps, and structural components must continue working in environments where access is limited and repairs take time. When a critical component fails underground, the machine stops, production stops, and reaching the failure can become a project of its own.
What the machines leave behind is the clearest measure of what they were capable of. The Tianma pit in Shanghai is 88 meters deep, with slopes requiring 99 anchor cables and 6,500 anchor bolts for stability. It was created through countless cycles of drilling, blasting, loading, crushing, and hauling. No single machine made the pit. It was formed by an entire mining system whose components survived long enough to keep production moving until the rock reserve was exhausted.
A mining machine begins as steel plate in a factory, passes through precision machining, sequential assembly, oversized transport, on-site commissioning, and finally arrives at the bench where it does the one thing it was designed to do: take abuse repeatedly without stopping. The central question was not how these machines are powerful. Power is straightforward. Add more engine displacement, more hydraulic flow, more steel. The harder question was how they survive. Survival in a mining environment is an engineering outcome built from 1,000 small decisions: the geometry of a bore, the insulation rating of a winding, the wear ratio of a tooth profile, the sequence in which components are assembled, the access clearance designed around a hydraulic. Every machine was designed around a version of the same constraint. It will be abused, it will wear, it will eventually fail, and when it does, the failure must happen at the intended location, the replacement must be possible in the field, and the machine must return to production in the shortest time the design allows. The questions left open are the ones the industry is currently working through. What happens when diesel gives way to battery electric in underground applications? How automation changes the maintenance model when there is no operator in the cab? And whether the materials and architectures developed for fossil fuel extraction translate to the mining loads that the energy transition itself will require. Thank you for watching. If you found it worth your time, there is more on this channel. Topics on large-scale engineering, infrastructure, construction, and the systems that move the world. Subscribe so you don't miss what's coming.